The following content
Yeah. Let me get check right here. I don't even know how to do this anymore. I forgot. Go to YouTube and get the chat link. Oh gosh. Oh boy. Should be good. All right. Okay. All right. Hello, everybody. Welcome back into the stream. I hope you're having a good day so far. As you can probably tell by my voice, I am still sick. Man, dude, I cannot shake this thing. It's brutal. I'm under like a cold and flu medicine in me like crazy. I tried to go on like a little walk today, and it turned into like a pretty like exhausting, hike, and honestly wasn't it really set me back. So that was all me. My bad, my bad. Because I was struggling there at the end, dude. Let me tell you, because I haven't had a lot of calories. I haven't had a lot of just movement in the past few days. Because man, I've been just wrecked. So I appreciate you guys hanging out with me just for a little bit today as we complete lecture 3 of our MIT 6.0002 course. Let me go ahead and start the recording for the follow along series for the channel. So I'm going to do that, and we'll do a little intro and we'll get started here. So I appreciate everybody being here. We're just on the bench, Tim. We're on the bench in street clothes, Tim. We're on the bench in street clothes, just supporting the team, coming back in. Just trying to get a ease our way back in by watching a lecture here. I figure we could at least sit down and watch a lecture together. Now that I can at least look somewhat presentable on camera, not like a complete just potato on the couch, just just dead and drool coming down, snot and all that jazz. But dude, your boy is still wrecked over here. Yeah, it's been rough, you guys. I don't know what I caught, but I luckily I caught it at the very last day of my project at work. So I was able to get that done. I toughed out the last day there, and I called it quits after half the day. I was like, I'm done after I got everything out. And then I took the rest of the week off, and dude, I've been just dead since. I haven't been playing really games. I haven't been streaming. So your boy is just in the slumps if he is not doing those things. At least he ain't lying to you guys. So let's go ahead and get the recording started for the YouTube here. So all right, cool. So we are going to be picking back up today with Lecture 3, Graph-theoretic Models for the MIT Introduction to Computational Thinking and Data Science course 6.0002 from fall 2016. This is Lecture 3 with Eric Grimson. We had Professor John in the past ones. So now we're going to be moving on to Mr. Eric for this one. So it's going to be nice and fun. This one might be a little bit more intensive, like more math and theoretical thinking. So maybe we'll see how this goes. And yeah, I appreciate you guys being here. If you guys are interested, I am doing this live. So if you guys want to follow along to the series live, you can go ahead and do so onto my YouTube channel and follow along daily around 7 p.m. PST as I stream and teach myself computer science daily. All right, let's go ahead and get into this video, you guys. So as I said before, this is lecture 3 of graph-theoretic models. I'm trying not to make too. Dude, it's been a while, you guys. I'm going to try to not make too many pauses. Man, my voice is chopped too. I feel like a goof. I'm going to try to not make too many pauses, but so we can kind of get through this one, as it might be a little bit more intense, and I don't want to really drag it on. And this is just going to be a just study harder. Where's that at? Where's that at? Just study harder. Oh no. Who said that? So yeah, let's go ahead and as we do a like up here. All right, here we go. All right, yeah. So if you guys are, let's get started, dude. I don't even know. Let's just go.
Welcome back. Over the last couple of lectures, we've been looking at optimization models. And the idea was, how do I find a way to optimize an objective function? It could be minimize or maximize it relative to a set of constraints. And we saw, or Professor Guttag showed you, that one of the ways that naturally falls out is by looking at trees, decision trees, where you pass your way through a tree, trying to figure out how to optimize that model. So today, we're going to generalize those trees into another whole broad class of models called graph-theoretic or graph models.
Let me know how the volume is,
use those
please.
to again look at how do we do optimization on those kinds of models.
Okay.
Just to remind you,
models.
there is a great piece of information in the text. There's the reading for today. And these, of course, be in the slides that you can download. So let's take a second just to reset again. What are we trying to do?
Again. Is he Canadian?
Generally, we're trying to build computational models. So what does that mean? The same way we could do a physical experiment or a social experiment or model, if you like, a physical system and a social system to both try and gather data and analyze it or to do predictions, we want to do the same thing computationally. We'd like to be able to build models in code that we can then run to predict effects, which we then might test with an actual physical experiment. And we've seen, for example, how you could take just the informal problem of choosing what to eat and turning it into an optimization problem. In this case, it was a version of something we called a knapsack problem.
Yep.
And how you could then use that to find code to solve it. And you've already seen two different general methods. You've seen greedy algorithms that just try and do the best thing at each stage. And you saw dynamic programming as an elegant solution to finding better ways to optimize this. We're going to now look at broadening the class of models to talk about graphs. So, obvious question is, what's a graph? A graph has two elements, two components. It has a set of nodes, sometimes called vertices, Those nodes probably are going to have some information associated with them. It could be as simple as it's a name. It could be more complicated. A node might represent a student record, the grades. And your graph might talk about putting together all of the grades for a class. Associated with that, we can't just, well, I should say, we could just have nodes, but that's kind of boring. We want to know what are the connections between the elements in my system.
Okay.
And so the second thing we're going to have is what we call edges, sometimes called arcs.
Edges.
And an edge will connect a pair of nodes. We're going to see two different ways in which we could build graphs using edges. The first one, the simple one, is an edge is going to be undirected. And actually, I should show this to you. So there's the idea of just nodes. Those nodes, as I said, might have information in them, just labels or names. They might have other information in them. When I want to connect them up, the connections could be undirected. If you want to think of it this way, it goes both ways. An edge connects two nodes together, and that allows sharing of information between both of them. In some cases, we're going to see that we actually want to use what we call a directed graph, sometimes
sharing
called a
of
digraph,
information.
in which case the edge has a direction.
Okay, hold on. Let's just quickly pause. So allow sharing of information between, right, two nodes. Let's see, here we go. So set of nodes at its vertices. Butchered that, my bad. Vertices might have properties associated with them. Okay. Let's quickly jot that down. Might have some properties. Let's just do italicized. Associated with them. And then edges, set of edges are arcs, right? We'll say here arcs. Nodes are vertices. Oh, so we'll say nodes, vertices. Okay. Uni or undirected graph. Okay, so undirected. Undirected. Right, this is graph. And then he has directed, right? Which is digraph. Interesting. What is that? Source, parent, and destination, child nodes. Okay, so this guy has source, parent, and right. And then it says unweighted or weighted. Okay, let's keep rolling here. Hey, hi, my name is Bai. How's it going, dude? Welcome back in. Just, yeah, get better at coding. We're just having fun and learning new things. You know, I often, I've been contemplating with myself, you know, should we go back and learn more and get a, you know, master's or whatnot? And I often think, you know, we could probably teach ourselves a large portion of the things, you know, within those courses ourselves. So that's what we're doing here. So we've been doing that for about a year on this channel. What's going on, dude? Hey, Baltona 444. Nice, dude. I appreciate you. Thanks for the love, man. Welcome in. Welcome in. Welcome, welcome, welcome. My name is Michael. Appreciate you guys for being here. Welcome in. You are. My name is Bai. You are. Hey, Eduardo. Welcome back in, my guy. All right. If you guys can't tell, I'm recovering from a sickness. So this is the warm-up stream back in. Let's keep going.
From a source to a destination, or some actually want to use what we call a directed graph, sometimes called a digraph. We're there, and that, as I said, might have information in them, just labels or names. They might have other information in them. When I want to connect them up, the connections could be undirected.
Undirected.
If you want to think of it this way, it goes both ways. An edge connects two nodes together, and that allows sharing of information between both of them. In some cases, we're going to see that we actually want to use what we call a directed graph, sometimes called a digraph, in which case the edge has a direction from a source to a destination,
source to a destination.
Sometimes from a parent to a child. And in this case, the information can only flow from the source to the child. Now, in the case I've drawn here, it looks like there's only ever a single directed edge between nodes. I could, in fact, have them going both directions, from source to destination, and a separate directed edge coming from the destination back to the source. And we'll see some examples of that. But I'm going to have edges. Final thing is, those edges could just be connections. But in some cases, we're going to put information on the edges. For example, weights. The weight might tell me how much effort is it going to take me to go.
Okay, so I'm going to quickly just take my screen cap here, and I'm going to screen cap this from lecture. It's a pretty crappy screen cap, but it'll get the job done. I want to keep these weights, keep these notes detailed for you guys. These notes are on my GitHub, link down in the description below. I keep them up to date live for all lectures I do, so you can find all my notes in there, and my Discord down below as well, completely for free. Everything I do here is for free for you guys. You know, if I'm getting it for free, then you guys should too. All right, let's keep rolling.
To go from a source to destination.
Hey,
One of
Diego,
the
how's
things
it
I
going,
want
my
to
guy?
see is I want to think about how do I pass through this graph, finding a path from one place to another.
Yeah.
For example, minimizing the cost associated with passing through the edges. Or how do I simply find a connection between two nodes in this graph?
Oh, like minimizing
So
costs,
graphs
like taking up their weight.
Composed
Okay.
of vertices or nodes. They're composed of edges or arcs. So why might we want them? Well, we're going to see, and you can probably already guess, there are lots of really useful relationships between entities. I might want to take a European vacation. After November 8th, I might really want to take a European vacation. So I'd like to know what are the possible ways by rail I can get from Paris to London. Well, I could pull out the schedule and look at it, but you could imagine, I hope, thinking about this as a graph. The nodes would be cities. The links would be rail links between them.
And like
then one of the things I might like to know is,
cost
first of all,
ticket.
can I get from Paris to London? And then secondly, what's the fastest way to do it, or the cheapest way to do it? So I'd like to explore that.
Yeah, okay. That's a
Second
good
example,
one.
as you can see on the list, drug discovery. Modeling a complex molecule in terms of the relationships between the pieces inside of it, and then asking questions like, what kind of energy would it take to convert this molecule into a different molecule? And how might I think about that as a graph problem?
That's cool.
Third and obvious one,
That's so
ancestral
cool.
relationships, family trees.
Yeah.
In most families, almost all families, they really
That's a
are
pretty
trees,
obvious one.
not graphs. Hopefully you don't come from a family that has strange loops in them. But family trees are,
That was a good joke.
no, I'm in trouble here today, aren't I? Family trees,
Oh,
stay
boy,
with me,
that was a good joke.
are a great demonstration of relationships because there
like
it's
that one.
directional edges, right? Parents have children, those children have children. And like I say, it comes in a natural way of thinking about traversing things in that tree. And in fact, trees are a special case of a graph. You've already seen decision trees in the last lecture, but basically, a special kind of directed graph is a tree. And the property of the tree is, as it says there, any pair of nodes are connected, if they are connected, by only a single path. There are no loops. There are no ways to go from one node, find a set of things that brings you back to that node. You can only have a single path to those points. And Professor Gotag used this, for example, to talk about solving the knapsack problem. A decision tree is a really nice way of finding that solution.
Hey,
Now,
Adele, how's it going, my guy?
I drew it this way. In computer science,
Yeah,
we
that's good
mostly
joke
use
content.
Australian trees. They're upside down. The roots are at the top, the leaves are at the bottom, because we want to think about starting at the beginning of the tree, which is typically something we call the root, and traversing it. But however you use it, trees are going to be a useful way of actually thinking about representing particular kinds of graphs.
Yeah.
Okay, so we're going to talk in a second about how to build graphs, but let's spend just a second about saying, so why are they useful?
Yeah, why?
And if you think about it, the world is full of lots of networks that are based on relationships that could be captured by a graph. You use them all the time. Some of you are using them right now. Computer networks. You want to send an email message from your machine to your friend at Stanford. That's going to get routed through a set of links to get there. So the network set up
Okay, social
by a
network.
series of routers that pass it along, sending
Okay.
something requires an
Mark.
algorithm that figures out the best way to actually move that around. There's a great local company started by an MIT professor called Akamai that thinks about how do you move web content around on the web. Again, it's a nice computer network problem. I've already talked about this. We're going to do some other examples. Transportation networks. Here, if you think about it, obvious thing is make the nodes cities, make the edges roads between them, and now questions are, can I get to San Jose if you like old songs, and what's the best way to get to San Jose even if you don't like old songs? A network problem. How do I analyze it? Financial networks, moving money around, easily modeled by a graph. Traditional networks, sewer, water, electrical, anything that distributes content, if you like, and a different kind of content in this way around. You want to model that in terms of how you think about flows in those networks. How do I maximize distribution of water in an appropriate way, given I've got certain capacities on different pipes, which would mean those edges in the graph would have different weights. And you get the idea. Political networks, criminal networks, social networks. One of the things we're going to see with graphs is that they can capture interesting relationships. So here's an example that's from that little website you can see there. You're welcome to go look at it. And this is a graph analyzing the Wizard of Oz. So what's been done here is the size of the node reflects the number of scenes in which a character shares dialogue. So you can see, obviously, Dorothy is the biggest node there.
Yeah.
The edges represent shared dialogue, so you can see who talks to whom in this graph. And then this group has done another thing, which I'm going to mention, we're not going to solve today, which is you can also do analysis on the graphs. And in fact, the color here is done something called a min-flow or max-cut problem, which is it's tried to identify which clusters in the graph tend to have a lot of interactions within that cluster, but not very many with other clusters. And you can kind of see there's some nice things here, right? If you can read it, this is all the people in Kansas. This is Glinda and the Munchkins in that part of Oz. There's another little cluster over here that I can't read, and a little cluster over there, and then the big cluster down here. But you can analyze the graph to pull out pieces on it. You can also notice, by the way, the book is probably misnamed. It's called The Wizard of Oz, but notice there's the wizard, who actually doesn't have a lot of interaction with the other people in the story. It's okay, literary choice. But the graph is representing interactions, and I could imagine searching.
I like this guy.
Things about what goes on.
Yeah, sure, Diego, drop in the Discord, my guy. Drop any community resources.
So why are they useful? We're going to see that not only do graphs capture relationships in these connected networks, but they're going to support inference. I'm going to be able to reason about them. And I want to set that up, and then we'll actually look at how might we build the graph. And so here are some ways in which I might want to do inference. Given a graph, I might say, is there a sequence of edges, of links between two elements? Is there a way to get from A to B? What are the sequence of edges I would use to get there?
Yeah.
More interesting question is, can I find the least expensive path, also known as the shortest path? If I want to get from Paris to London, I might like to do it in the least amount of time. What are the set of choices I want to make to get there?
Yeah.
The third graph problem used a lot is called the graph partition problem. Everything I've shown so far, actually not quite, the first example didn't have it. You might think of all the nodes having some connection to every other node, but that may not be true. There may actually be graphs where I've got a set of connected elements and another component with no connections between them. Can I find those? That's called the graph partition problem. How do I separate the graph out into connected sets of elements? And then the one that we just showed, called the min-cut max flow problem, is there an efficient way to separate out the highly connected elements, the things that interact a lot, and separate out how many of those kinds of subgraphs, if you like, are there inside of my graph? All right, let me show you a motivation for graphs, and then we'll build them.
They need to
I
flash
use graph theory every day.
Slides on the screen. Show us
I'm
the
a
slides.
math nut. It's okay, but I use graph theory every day. You may as well if you commute, because I use it to figure out how to get from.
Let me really quickly here. Extra slides. An extra 3. I don't know. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. Okay, let me just go here then real quick.
From my home in Lexington down here to Cambridge. And I use a nice little system called Waze. It's a great way of doing this, which does graph theory inside of it. So how do I get to my office? Well, I'm going to model the road system using a directed graph, a digraph. Directed graph because streets can be one way, and so I may only have a single direction there. And the idea is I'm going to simply let my nodes or my vertices be points where I have intersections. There are places where I can make a choice or places where I have terminals, things I'm going to end up in. The edges would just be the connections between points, the roads on which I can drive. Some Boston drivers have a different kind of digraph in which they don't care whether that road is drivable or not, they just go on it. You may have seen some of these, but I want to keep my graphs as real roads that I can drive on. And I'm not going to go against the one-way sign. Each edge will have a weight. Here I actually have some choices. All right, the obvious one,
Okay.
the one that Waze probably uses,
Expected
is
time to
something
get
like,
to the source
what's the
node.
expected time between a source and a destination node? How long do I expect it to take me to get from this point to that? And then as you can see, I'm going to try and find overall what's the best way to get around it. You could pick just distance.
Distance
the
between
distance
source
between
and
the two?
destination.
And while there's a relationship here, it's not direct because it'll depend on traffic on it. Or you could take something
Average speed
even
of travel.
funkier, like what's the average speed of travel between the source and destination node? And once I've got the graph, then I'm going to solve an optimization problem. What's the shortest wait between my house
what's going
and
on,
my office
Austin?
that gets me into work?
Welcome
You
back,
make a
dude.
choice here. As I said, a commercial system like Waze uses this one. My wife and I actually have arguments about commuting because she's a firm believer in the second one, just shortest distance. I actually like the third one because I get anxious when I'm driving.
So Waze uses time.
And so as long as I feel like I'm making progress, I like it. So even though, I may be serpentining all the way through the back roads of Cambridge, if I'm driving fast, I feel like I'm getting there. So I like optimizing this bottom one down there. And if you see me on the road, you'll know why I say that.
I like
And then
doing least
get out of the way.
miles because that's what you got to also think of car depreciation.
Thinking about navigation through systems actually gives us a little bit of
kilometers
history because, in
for
fact, the
y'all
very
international
first
folks.
reported use of graph theory was exactly
American
this
here,
problem.
sorry.
Early 1700s is called the Bridges of Konigsberg.
We got
Konigsberg
an
is a
American
city that
here.
has a set of islands and rivers in it. There are 7 bridges that connect up those islands. And the question that was posed is it possible to take a walk that traverses each of the 7 bridges exactly once? So could you take a walk where you go over each bridge exactly once? I'm showing you this because it lets us think about how to, in fact, capture things in a model. This problem was solved by a great Swiss mathematician, Leonhard Euler. And here's what he said. Make each
Okay, so this is a big thing here. Okay. So let's go Leon. Let me know in chat if you've heard of this model before. You guys heard of this model? This is a popular one. Each island is a node. Right? Each bridge an undirected edge, which means that it can go both ways. Right? Model abstracts away irrelevant details. So this is kind of a key one here. Model abstracts away irrelevant ERRELEVANT details, right? Like size of islands and lengths of bridge, right? is there a path that contains each edge exactly once? No. And we'll say, I guess, is there a path that contains each edge exact? Watch out, Miss Kitty. Sorry. Exactly once. And then we say no. Okay, interesting. Hey, Formidable, how's it going, my guy? Cheek, how's it going? Chico. Okay. So we got this guy's model here. Oops. I'll bring these back. All right, let's keep going here. Let's keep rolling, let's keep rolling.
Make each island a node. Each bridge is just an undirected edge. And notice in doing that, he's abstracted away irrelevant details. You don't care what the size of the island is. You don't care how long the bridges are. You simply want to think about what are the connections here. And then you can ask a question. In this graph, is it possible to find a way to walk through it so that you go through each edge exactly once? And as Euler showed, the answer is no. And if you're curious, go look it up on Wikipedia. There's a nice, elegant solution to why that's the case. But here's what we're going to do. We're going to use those graphs to think about these kinds of problems. And in fact, the examples I'm going to show you are going to be shortest path problems. So with that, let's turn to actually building a graph and then thinking about how we're going to use it. So we're going to start by constructing graphs. And then what we're going to do is show how we can build search algorithms on top of those graphs. And I hope that that flicker is going to go away here soon. Here we go.
All right.
So to build a graph.
Buckle up, boys. Ladies and
Actually, I
gents.
shouldn't have put this slide up so fast. I've got lots of choices here. If I'm thinking about maps, one way to build a graph would really just be build something with latitude and longitude on it. But as we've already seen, we'd like to extract things away from the graphs. And so a natural choice is to say, let's represent the nodes in the graph just as objects. I'm going to use classes for these. So here's my definition of a node. It's pretty straightforward.
We're ready for this.
I'm going to assume that the only information for now I store in a node is just a name, which I'm going to assume is a string.
All right.
So I've got a class definition for node. It inherits from the base Python object class. I need ways to create instances of nodes, so I've got an init function. And I'm simply going to store inside each instance, in other words, inside of self, under the variable name, whatever I passed in as the name of that node. Of course, if I got ways to create things with a name, I need to get them back out, so I've got a way of selecting it back out. If I ask an instance of a node, what's your name? By calling getName, it will return that value. And to print things out, I'm just going to print out the name. This is pretty straightforward. This, of course, lets me now create as many nodes as I would like. Edges, well, an edge connects up two nodes. So again, I can do a fairly straightforward construction of a class. Again, it's going to inherit from the base Python object. To create an instance of an edge, I'm going to make an assumption, an important one which we're going to come back to. And the assumption...
Man, he's moving quick. He's moving quick. Let's get caught back up here. Okay, so let's just get this jotted down real fast. All right, so it takes in this class, this node object, right, with Python object-oriented programming as a class. We're just going to have a name parameter or an instance variable that we're going to assign as just self.name, right, is equal to name. And then we're going to have two functions associated with this, two, doesn't look like class methods, but just instance methods associated with this, such as getter functions for getName, or one get function, sorry, which just takes in self and returns that of self.name. right? And then we return, my fault. And then we would just have, it's going to define just a dunder stir here. And this is just a, when you call print, right, this was what the primary or the primary constructor is for, that will, default onto the print call, right, for this object. So when you call print on an object itself, it will return in display out self name, right, as its kind of string representation. Now we also know that the repr, REPR, dunder repr, that one also will be kind of like a secondary fallback. That one's more for like class reconstruction in string format. Okay, let's keep rolling here.
Assumption is that the arguments passed in, source and destination.
Okay, here we go. So now we got a class edge here, right? Right, and the class edge just takes in source and destination, and then has get source, get destination. So pretty easy. So let's just quickly bust this out. Pause. Let's go here, pi, and then do class. Well, let's do here. So class edge, right, which takes in an object. And let's define its initialization. So on instantiation of this object, we're going to have a source and a destination as required instance parameters, to create this object. We're going to assign those as just self of each, right? And then I'll just, for time's sake, copy that down, and then go here, edge, and then let's make this edge as well. Or sorry, this is destination, my fault. Oh, what's going on here, Mike? Destination. Okay, so then we have a getter. So let's define a def get source, which will be just on self, and we'll return self dot source. And then we also have a def get destination given self, right? And then we're going to return self.dest. And then we have a stir representation of this class given self, right? Ooh, my fault, you guys. We're going to return self.source, right, dot get name, right, of the source node, plus, right, we're going to concatenate a string of a arrow, right, source node 2, kind of like to have that source node arrow to the, and then we'll have a, they do a backslash plus here. I think it's just because it's on a new line. So I'm just going to say plus self dot destination dot get name. All right. Cool. So pretty easy. This is very basic kind of object structure here. Nothing crazy. Let's keep rolling.
Are nodes, not names, the nodes themselves, the actual instances of the object class. And what will I do inside of the edge? I'm going to set internal variables for each instance of the edge, source and destination. We're going to point to those nodes, to those objects that I created out of the node class. Next two things are straightforward. I can get those things back out. And then the final piece is, when I want to print out what an edge looks like, I'm going to ask that it print out the name of the source, and then an arrow, and then the name of the destination. So notice what I do there. Given an instance of an edge, I can print it, and it will get the source, or the node associated with source inside this instance, get for that the get name method, and then call it. Notice the open close paren there to actually call it. What does that do? It says, inside the edge, I've got something that points to a node. I get that node. I take the method associated with it, and I call it. That returns the string. And then I glue that together with the arrow. I do the same thing on the destination, and I just print it out. Pretty straightforward, hopefully.
Yeah, I got you.
Okay, now I have to make a decision about the graph. I'm going to start with digraphs.
Hopefully people in the
I need to
seats
think
in
about how I
the
might
back.
represent the graph.
Oh my
I can
gosh.
create nodes, I create edges, but I got to
They
bring
don't know
them
what's
all
going
together.
on.
So I'll remind you, a digraph is a directed graph. The edges pass in only one direction. And here's one way I could do it. Given all the sources and all the destinations, I could just create a big matrix called an adjacency matrix. The rows would be all the sources. The columns would be all the destinations. And then in a particular spot in the matrix, if there is an edge between a source and a destination, I'd just put a 1. Otherwise, I'd put a 0. Note, by the way, because it's a directed graph, it's not symmetric. There might be a 1 between S and D, but not between D and S, unless there are edges both ways. This would be a perfectly reasonable way to represent a graph, but not the most convenient one. I'd have to go into the matrix to look things up. It may also not be a very efficient way of representing things. For example, if there are very few edges in the graph, I could have a huge matrix with mostly zeros, and that's not the most effective way to do it. So I'm going to use an alternative called an adjacency list.
Adjacency list.
The idea here is for every node in the graph, I'm going to associate with it a list of destinations. That is, for a node, what are the places I can reach with a single edge? Okay, so let's see what that does if we want to build it. And yes, there's a lot of code here, but it's pretty easy to look through, I hope. Here's the choice I'm going to make. Again, what's a graph? It's a set of nodes. It's a set of edges. I'm going to have a way of putting nodes into the graph, and I'm going to choose to, when I put a node into the graph, to store it as a key in a dictionary. Okay?
Okay.
When I initialize a graph, I'm just going to set this internal variable edges
To a
to
blank
be an empty
dictionary.
dictionary. And the second part of it is when I add an edge to the graph between
Oh, this is
two
easy.
nodes,
Okay.
from a source to a destination, I'm going to take that point in the
We've done this
dictionary
in our
associated
projects.
with the source, it's a key,
Naturally.
and associated with it, I'm going to just have a list
Naturally.
of the nodes I can reach
Look at
from
that.
edges from that source.
Let's go.
So notice what happens here. If I want to add a node, again, remember, it's a node, not an edge. I'll first check to make sure that it's not
If it's
already
in
in the
edges.
dictionary. That little loop is basic, or that if is saying if it's in this set of keys, it'll return true, and I'm going to complain. I'm trying to copy a node or duplicate a node.
Yeah.
Otherwise, notice what I do. When I put a node into the dictionary, I go into that dictionary edges. I create an entry with the key that is the node.
Of the node.
And the value I put in there is initially an empty list. I'm going to say one more piece carefully. It's a node, not a name. And that's okay in Python. It is literally, the key is the node itself. It's an object. That's what I'd like. Right, what if I want to add an edge? Well, an edge is going to go from a source to a destination node. So I'm going to get out from the edge the source piece. I'm going to get out from the edge the destination piece by calling those methods. Again, notice the open-close paren, which takes the method and actually calls it. Because remember, an edge was an object itself. Given those, I'll check to make sure that they are both in the dictionary. That is, I've already added them to the graph. I can't make a connection between things that aren't in the graph.
Yeah.
And then notice the nice little thing I do. Presuming I have both of them in the dictionary, I take the dictionary, I index into it with the source node. That gives me a key into the dictionary. I pull out the entry at that point, which is a list.
Yeah. Okay.
So I created them up here. And I add the destination node
Just
with
to it.
append into the list, stick it back in. So this now captures what I said I wanted to do. The nodes are represented as keys in the dictionary, and the edges are represented by destinations as values in the list associated with the key. So you can see if I want to see, is there an edge between a source and a destination? I would look
Rudy,
up under
there's
source
Harvard
in the dictionary and then
CS50P.
check in the list
You should
to
check
see if
that
the
out.
destination is there. Okay, the rest of this then follows pretty straightforwardly. If I want to get all the children of a particular node, I just go into the dictionary edges and look up the value associated with that node. It gives me back the list I've got all the things I can reach from that particular node. If I want to know if a node is in the graph, I just search over the keys of the dictionary. It'll either return true or false. If I want to get a node by its name, which is going to be probably more convenient than trying to keep track of all the nodes, well, I could pass in a name as a string, and what will I do? I'll just search over all the keys in the dictionary using the getName method associated with it. There's the call, and checking to see if it's the thing I'm looking for. And if it is, I'll return M. I'll return the node itself. What about this thing here? It might bother you a little bit. Wait a minute, that raise, isn't it always going to throw an error? No, because I'm going to go through this loop first, and if I actually find a node, that return is going to pop me out of the call and return the node. So I'll only ever get to this
if you don't ever
in fact
return
I
N.
couldn't find anything here.
Yeah.
So it's an appropriate way to simply raise the error to say, if I get to this point, couldn't find it, raise an error to say the node's not there.
It's the default.
The last piece looks a little funky, although you may have seen this. I like to print out information about a graph. And I made a choice, which is I'm going to print out all of the links in the graph.
You're just looping through it.
So I'm going to set up a string initially here that's empty. And then I'm going to loop over every key in the dictionary, every node in the graph. And for each one, I'm going to look at all the destinations. So notice, I take the dictionary, I look up the things at that point. That's a list. I loop over that. And I'm just going to add into result the name of the source, an arrow, and the name of the destination, followed by a carriage return. I'll show you an example in a second, but I'm simply walking down the graph saying, for each source, what can it reach? I'll print them all out. And then I'll return everything but the last element. I'm going to throw away the last carriage return because I don't really need it. So let me show you an example here, trusting that my Python has come up the way I wanted it to. So I'm going to load that in, ignore that for the moment, and I'm going to set G to, I've got something we're going to come back to in a second.
I like how they run in live in
a graph.
lecture. That's so cool.
If I print out G, it prints out, in this case, all of the links from source to destination, each one on a new line. Okay. So I can create the graphs. That was digraphs. Suppose I actually want to get a graph. Well, I'm going to make it as a subclass of digraph. And in particular, the only thing I'm going to do is I'm going to shadow the add edge method of digraphs.
So you're just going to add a custom,
if I make a graph, if I ask it
everything
to add edges,
of digraph,
use this
but it has this add edge now, right?
And what am I going to do? I know in a graph, I could have
it overrides add edge to this.
So, given an edge that I want to add into this graph, I'll use the method from the digraph class, and I'll add an edge going from source to destination.
And then you'll link the reverse.
And then I'll just create an edge the other direction. Destination becomes source, source becomes destination, and I'll add that into the graph. Nice and easy. Straightforward to do. And this is kind of nice.
He's moving quick, so if people aren't familiar with object-oriented in the lecture hall, they're probably shaking right now.
And you might say, well, wait a minute, why did I pick graph to be
in Python? If they're not familiar with classes in Python, they're probably like shaking in their boots.
Reasonable question. Yeah. And you actually know the answer. You've seen this before. One of the things I'd like to have is the property that if the client code works correctly using an instance of the bigger type, it should also work correctly when it's using an instance of the subtype substituted in, which is another way of saying anything that works for digraph will also work for a graph, but not vice versa. And as a consequence, it's easier to make the graph a subclass of digraph. Notice the other thing that's nice here, one little piece of code. Just change what it means to make an edge. Everything else is
right. That's just parent-child relationship.
Also notice you've
inheritance.
Seen this before, how we nicely inherit the method from the subclass by explicitly
from the
digraph class, get
inheritance
the add edge method and apply it. Okay, so we can build graphs. We're going to do that in a second. Let's turn now to thinking about, I'd like to search on a graph. And
I'll go back through in my notes and I'll get these classes later.
I'd like to find the best path home. So what's the shortest path from one node to another? And that shortest path initially will just be the shortest sequence of steps.
Shortest number of edges you touch, right?
I hope I'm not having a little attack here. You just saw that screen blank out, right? But the shortest path of steps with the property that the source of the first edge is the starting point.
It's like
The
a recursive
destination
problem
of the last
taking
edge,
min
the thing I'm trying to get
of
to. And
either.
for any edge in between, if I go in my first edge from source to say node 1, the next edge has that destination as its source. So there's simply a chain that says I can go from here to here to here to here to get all the way through. And I'd like to find what's the shortest number of steps, edges like that, that'll get me from source to destination. Ultimately, if those edges have weights on them, the optimization problem I'd like to solve is what's the shortest weighted path, the shortest amount of work I have to do to get to those places.
Yeah, you'd have to
and
compare
if we can solve
to
one, we'll see that we can solve the other one pretty
some sort of
straightforward. And we've
maybe
already
like-
seen examples of shortest path problems. Clearly finding a route navigation is one. Designing communication networks is another great example of a shortest path problem.
like map or something.
You'd like your message to get you to your friend as quickly as possible and not go as many times around the world before it gets there. So what's the shortest amount of time or the fewest links I have to use to get there? Lots of nice biological problems that also capture this piece. So here's an example, and we're going to use this to look at two different kinds of algorithms to solve this problem.
What's going on,
This is a
Prism?
little navigation problem.
Hey,
from a set
thunder,
of cities.
thunder,
Think of
thunder.
it as flight paths. If you're from Arizona, my apologies, but once you get to Phoenix, you can't get out of there unless you grow from the ashes, I guess. But, you know, it's a way of dealing with how to get around in places. And to think about this, here's the representation that we'd have in the graph. The
Sounds like the
adjacency
NBA
graph
team,
here,
except
our
for-
adjacency list here is from Boston, I can get to Providence, I can get to New York. From Providence, I can get to Boston, I can get to New York. From New York, I can only get to Chicago. Chicago, I can go to Denver or Phoenix. Denver, I can go to Phoenix or New York. And from LA, you
Shout
can
out
only
Boston,
come back to
Tim.
Boston. And Phoenix has no exits out of it. So there's that representation. I just want to let you see that, right? There are the keys in the dictionary. They're all the nodes. And there, each one of those lists is a set of edges from the source to the destination. Okay. How would I build this?
Oh boy.
Well, this is the code I just ran. I just want to show it to you. I noticed, by the way, in the slides I distributed earlier, there's missing, the
Just
return
adding
key is
edges
missing
between
there. If you want to
nodes.
correct it, I'll repost it later on. I'm going to create a little function that's going to build a city graph. I'm going to pass in a type of graph which I will then call to create it. So I could make this as a digraph. I could make it as a graph. I'm going to start off with it as a digraph. And then notice what I do here. I just run over a little loop, set
Digraph
of
meaning
names,
that only
creating
one
a
can't
node
return
with that name, and then adding it into
back,
the graph.
only one direction, unidirectional.
Right? So node is a
Parent
class
to child.
instance that creates, or a class definition that creates an instance. And once I've got that, add node is a method on the graph. It will simply add it in. And then this set here is simply adding in the edges. And I can do that. I'm capturing what I had on that previous slide. I'm going to give a name to get node. It will get out the actual node. And I use that coming out of the graph G. I do the same thing with the get node from graph G for Providence. And then I make an edge out of that. And then I use the method from the graph to add the edge.
Okay, so what's going on here is, let's see. So he's saying G is a variable housing his just graph type, which is you would whatever you're inheriting from. So he said in the lecture he's inheriting from his digraph. So it's unidirectional, right? So that's what G is housing. It's just this graph object. For every name in this tuple of names, right, we're going to do g.addNode, so the add node method for this graph, and create a node for every name. Okay, cool. So we're just going to create nodes, and boom. And then at the end of that list, at the end of that loop, we're going to add edges between a few nodes. So we're going to get the node of Boston, get the node of Providence, create an edge between those of source and destination, and then create an edge. And so we're just going to do that for a few places. Pretty simple. Pretty simple, you guys. Nothing crazy. All right, we're all on the same page.
If this looks like a lot of code, yeah, it's a lot of words, but it's
Hey,
pretty
Nick.
straightforward. I'm literally creating
How's it going,
nodes
Nick? I
with
like
the
that.
names using the appropriate methods, creating an edge, adding it into the graph. And when I'm done, I'm just going to return the graph G.
Nickez.
Okay, now I want to find shortest path. And I'm going to show you two techniques for doing this. First one's called depth first search. It's similar to something Professor Goodtag showed.
Okay, here we go. Here we go, leak code boys. Tim, wake up. Tim, leak code. Here we go. So I'll go back through you guys, and I'll get these. I'll copy these classes into the notes here. I don't think it's super kind of relevant for us to. We understand what the class is doing, and so we'll go back through and copy it down later, which will also help reinforce the concepts, right? Going back at a different time in a different sitting and looking back over the notes. So that'll be a good reinforcement, but it's not really super necessary for watching the lecture right now, as long as we understand what's going on. Okay, so find the shortest path. All right, so algorithm 1, depth first search. Here we go. We learned about a couple of these in our DSA and Python book. If you guys aren't familiar, we read on the channel a data structures and algorithms book in Python. We're on chapter 11 of this book. So this gave us a really good introduction to warm up into Python, object-oriented programming for like more advanced kind of algorithms and things like that, getting into like recursion and kind of bridging those gaps for us. We read all the way up to chapter 11, stacks, decks, queues, trees, tries, all that kind of jazz, linked lists. So we got some good that help us to be able to solve up to 100 leak code problems thus far. But we are continuing on. So this lecture is pretty good for kind of reinforcing these concepts and really kind of sending them home. There we go. Let's keep on. So depth first search. Right, so this is going to go to the depth of every branch basically first, starting from the leftmost all the way over to the rightmost, and then in that way, right? Whereas BFS, breadth first search, is row by row, like depth by depth, all the nodes in the depth, left to right. If I remember, similar to left first, depth first method of enumerating of a search tree, main difference is the graph might have cycles, so we must keep track of what nodes we have visited to avoid going in infinite loops. Note that we are using divide and conquer if we can find a path from a source to... Okay, right, so you start at an initial node. You consider all the edges that leave that node in some order. You follow the first edge and check to see if at goal node, I'll say goal node, target node, whatever, like your base case, right, or something. Or no, like whatever node you're trying to perform operations on. If not, repeat the process from new node, continue until either find goal node or run out of options. We'll say when run out of options, backtrack to the previous node and try the next edge, repeating this process. Baseball at 5 a.m. Wow, wow, wow. Sticking the crane. When are you gonna hit a grand slam at Deming Field? That's probably condemned again by now. Hey, Coffee, how's it going? Thanks for joining me on Twitch, my guys. If you guys are on Twitch and aren't followed, I'd really appreciate if you guys could. If you guys are on YouTube, subscribe. Thank you guys so much. Oh, we crossed over 2680 here, so thank you guys so much. Yeah, these courses are free for MIT OpenCourseWare. MIT provides their courses for free here for some of them, and so this is one of them that we're going to be doing from 2006. We're on lecture 3 here, and we're documenting the entire thing live here.
I showed you when you sort of took the leftmost, depth first method in terms of a search tree. The one trick here is because I've got graphs, not trees, there are the potential for loops, so I'm simply going to keep track of what's in the path, and I'm never going to go back to a node that's already in the path. So I don't just run in circles going from New York to Boston to New York to Boston constantly. All right? So the second thing I'm going to do here is I'm going to take advantage of a problem you've seen before, which is this is literally a version of divide and conquer. What does that mean? If I want to find a path from a source node to destination node, if I can find a path to some intermediate node, source to intermediate, and then I find a path from intermediate to destination, the combination is obviously a path the entire way.
That was rough,
so
my guy.
Recursively, I can just break this down into simpler and simpler versions of that search problem. So here's the idea behind depth first search.
West Coast, USA,
Start off with that
Coffee.
source node, that initial node. I'm going to look at all the edges that leave that node in some order, however order it was put into the system. And I'm going to follow the first edge. I'll check to see if I'm at the right location. If I am, I'm done. If I'm not, I'm going to follow the first edge out of that node. So I'm actually creating a little loop here. And I'm going to keep doing that until I either find the goal node or I run out of options. So let me show you an example.
Okay, let's look here.
I've got a little search tree here, very simple one. There's my source, there's my destination. In depth first, I'm going to start at the source and go down the first path. See if I'm at the right place. I'm not. So I'm going to take the first path out of here, which might be that one. See if I'm in the right place. Actually, let me not do it that way. Let me do it this way.
Left to right, depth first, right?
Am I in the right place? I'm not.
Yeah.
So I'm going to take the first path out of this one, which gets me there. I'm still not in the right place, so I'm going to take the first path out of that one. And you can see why it's called depth first. I'm going as deep, if you like, in this graph as I can, from here to there to there to there.
So now I need to backtrack, right?
At this stage, I'm stuck. There's no place to go to, so I'm going to go back to this node and say, is there another edge? Which in this case, there isn't, so I'll go back to here. There's not another edge. Go back to here. There is another edge, so I'm going to go this direction. And from here, I'll look down there. Again, notice I'm now going depth first down the next chain.
I've been in this
Nothing
loop
from
now.
here, I backtrack. There's nothing from there, I backtrack over to here. There's no additional choices there, so I'll go all the way back to here to follow that one. And then I'll go down this one again, backtrack, and eventually I find...
But you've already seen that node, right? So can you exit early?
Depth first, following my way down.
Or maybe you need to find all possible paths.
So let's write the code for it. Yes, ma'am.
He's so excited someone asked a question. He looks so happy.
The question is which node or which edge do I choose? Is however I stored it in the system. So since it's a list, I'm going to just make that choice. I could have other ways of deciding it, but think of it as, yeah, essentially random.
Like left first versus right?
Okay, let's look at the code. Don't panic. It's not as bad as it looks. It actually just captures that idea. Ignore for the moment this down here. It's just going to set it up. Depth first search, I'm going to give it a graph, a start node, an end node, and a path that got me to that start node, which initially is just going to be an empty list. Something that tells me what's the shortest path I've found so far, which would be my best solution, and then just a little flag here if I want to print out things along the way. What do? I set up path to add in the start node. So if path initially is an empty list, the first time around it's just, here's the node I'm at. I print out some stuff, and then I say, see if I'm done. I'm just going to stay at home. I'm not going to go anywhere. Unlikely to happen, but you'll see recursively why this is going to be nice. If I'm not done, then notice the loop. I'm going to loop over all the children of the start node. Those are the edges I can reach, the nodes I can reach with a single edge. I pick the first one, and in answer to the question, in this case it would be the order in which I stored it in the list. I just pick that one up. I then say, let's make sure it's not already in the path, because I want to avoid loops. And assuming it isn't, and assuming I don't yet have a solution, or the best solution I have is smaller than what I've done so far, oh, cool. Just do the same search. So notice there's that nice recursion, right? I'm going to explore. I just picked the first option out of that first node, and the first thing I do is try and see if there's a path from that node using the same thing. So it's literally like I picked this one. I don't care about those other edges. I'm going to try and take this search down.
Yeah.
When it comes back with a solution, as long as there is a solution,
yeah.
so that's my best solution so far.
Blank stare. Yeah.
And then I go back around. Now, this last little piece here is just if, in fact, the node's already in the path, I'm just going to print something out that says don't keep doing it because you don't need to keep going on. And I'm going to do that loop, taking all the paths down until it comes back. And only at that stage do I go to the next portion around this loop. The piece down here just sets this up, calling it with an initial empty list for path and no solution for shortest. So it's just a nice way of putting a wrap around it that gets things started up. This may look a little funky, may look a little bit twisted. So let's see if it actually does what we'd expect it to. And to do that, I'm just going to build a little test function. I'm going to build that city graph. I'm just going to call shortest path. I'm going to print it out. And I'd like to see, is there a way to get from Boston to Chicago? So let's go back over to my Python and try that out. And I've got a call for that. Oh, and it prints out. I start off. Oh, so I did it the wrong way. It's from Chicago to Boston. Yes, Chicago to Denver to Phoenix. From Denver to New York. Comes back and says, I've already visited. Basically concludes I can't get from Chicago to Boston. It's just printing out each stage. Let's actually look at that a little more carefully to see how it got there. So there's my example. There's the adjacency list, and here's what happens. I start off in Chicago. So that's my first node. From Chicago, the first edge goes to Denver. Denver's not what I'm looking for. But since I'm in Denver, recursively, I'm going to call it again. So the first edge out of there is to Phoenix. Again, sorry if you're from Arizona and Phoenix, there's nowhere to go.
Backtrack.
So I'm going to have to backtrack.
To Denver.
And that will take me back up
New York.
to Denver. And I look at the next edge. Takes me to New York.
Then I go to
From New
Chicago.
York, I'd like to go to Chicago. But oh, that's nice. Because remember that first check, it says, is Chicago already in the path? It is. I don't want to loop. Because otherwise, I'm simply going to go around and around and around here. And it may be good for frequent flyer miles, but it's not a great way to get to where you're trying to go. So I break out of it. And now what else do I have left? Chicago to Denver, I've explored. I look at Chicago to Phoenix. From Phoenix, there's nowhere to go. I go back up to Chicago. There are no more paths. I'm done.
There is no path to Chicago.
OK. Now, turns out you can actually get somewhere in this graph. So here's just another example. I'm simply going to show you if I want to go from Boston to Phoenix, notice the set of stages. And you can see, notice how at each stage it tends to be growing. That's that depth first. I'm exploring the edges. I find a path. That's great. But is it the shortest path? I don't know. So having found that path, I try and take the next branch, which finds a loop. And I keep moving through this, finding paths until I look at all the possible paths and I actually return the shortest path. You can try running the code on it, but what I want you to see is again this idea that I can explore it, but in fact I'm going to have to explore it in a particular order. But there's depth first search. It will find a solution for me. Alternative is what's called breadth first search.
Breadth first search. Here we go.
Almost the same. Again, I'm going to start off with initial load. I'm going to look at all the edges that leave that node in some order. I'm going to follow the first edge as before and see if I'm at the right place. If I'm not, I'm going to follow the next edge and do the same thing. So whereas this went down through the tree as deeply as I could, or the graph, in breadth first, I'm going to start off taking that edge as before. I'm not done. I'm going to keep track of that in case I want to explore more of it, but I'm going to go back over here and follow that edge. I'm not done. Again, I'll keep track of that, but I'll come back up here and explore that one. And oh, cool. I found a solution in 3 steps. I reached the destination. And notice, because I'm exploring all the paths of length 1 before I get to paths of length 2, once I find a solution, I can stop, because I know it's the shortest path. Any other path through here would be longer than that particular solution. So the loop here is a little different. I'm looking over all the paths of length 1, then all the paths of length 2. And the one thing I'm going to have to do is I'm going to have to keep track of the remaining options here in case I have to come down to them. Because if I didn't find it at the first level, then I come down here and look at things of length 2. Okay? So let's build that code. Breadth first search, or BFS. Again, a graph, a start and an end node, something that would just print things out as I go along. My initial path is just the start point.
Start point on the list.
But now I've got to keep track of what are the paths that I have yet to explore. And so for that, I'm going to create something called a queue. And a queue is going to be a list of paths. Remember, a path is a list of nodes. A queue is going to be a list of paths. So the initial queue is just where I've started. And then as long as I've got something still to explore and I haven't found a solution, I'm going to pop off the queue the oldest element, the thing at the beginning. That's my temporary path. I'll print out some information about it. And then I'll grab the last element of that path. That's the last point in that path. And I'll now explore. Is it the thing I'm looking for? In which case I'm done. I'll return the path. Otherwise, for each node that you can reach from that point, create a new path by adding that on the end of this path and add it into the queue at the end of the queue. So I'm going to keep looping around here until I either find a solution here, which I'll return, and if I get through all of it, I'm going to return none.
Yeah, we just solved one of these.
Right there, there's that nice thing where once I find a solution, I know it's the shortest thing, I can stop. Again, let's look at an example of this. I'm going to go back over to Python where I've got a version of this. I'm going to comment that out. And down here in breadth first search, I've actually added a little piece of code that I don't have in the handout that's going to print out the queue as well so we can see what happens when we call this.
Run out of
so let's take a look at it. My initial call, there's one thing in the queue, it's just Boston. Started in Boston. So the best path, or the current path, is to start in Boston. I take that element off the queue and I say, what are the things I can reach from Boston? Oh, nice. I put 2 things in. I can get from Boston to Providence. I can get from Boston to New York. The top thing's gone off the queue. I popped it. I've replaced it with 2 things there. I take this and say, OK, from Boston to Providence, where can I get from Providence? Oh, I can get to New York, so I put that in the queue.
You just go through the output.
This has gone off. That one is still there. And I do that because I haven't yet reached the thing I'm looking for, which was, I think, Phoenix I was trying to get to. And you can see at each stage, I'm taking the top thing off the queue, asking for all the things that I can get to, and adding them to it. And notice, in some cases, it may be more than one. For example, which one do I want here? Right here. If I take Boston, New York to Chicago. From Chicago, I can get to Denver. So there's one new path. I can also get to Phoenix. There's a second new path. Also notice how they're only growing slowly as I build them out. And in fact, if we go back, we can see that nicely by looking at what happens if we were to actually trace this along. So Boston to Phoenix. I start at Boston, then I look at that, and then that. Those are all the paths of length 1. Having exhausted those, oh, nice. I'm looking at paths of length 2, and then paths of length 3, and then paths of length 4 until I found the one that I wanted. And here's one other way of looking at it. Breadth first says, I look at each path of length 1, and then, oh yes, I avoid the loop. I look at each path of length 2, then paths of length 3, until I actually find the solution. Subtle difference, different performance. Depth first, I'm always following the next available edge until I get stuck and I backtrack. Breadth first, I'm always exploring the next equal length option. And I just have to keep track in that queue of the things I have left to do as I walk my way through. What about weighted shortest path? Well, as the mathematicians say, we leave this as an easy exercise for the reader. It's a little unfair. The idea would be, imagine on my edges, it's not just a step, but I have a weight. Flying to LA is a little longer than flying from Boston to New York. What I'd like to do is do the same kind of optimization, but now just minimizing the sum of the weights on the edges, not the number of edges. As you might guess, depth-first search is easily modified to do this. The cost now would simply be what's the sum of those weights. And again, I would have to search all possible options till I find a solution. Unfortunately, breadth-first search can't easily be modified because the shortest weighted path may have many more than the minimum number of loops, and I'd have to think about how to adjust it to make that happen. But to pull it together, here's a new model. Graphs. Great
Graphs
way
are
of
cool.
representing
Here we
networks,
go.
collections of
Wrapping it
entities
up.
with relationships between them. There are lots of nice graph optimization problems, and we've just shown you 2 examples of that. But we'll come back to more examples as we go along. And with that, we'll see you next time.
All right. Woo! Nice. I appreciate you guys hanging out with me here as we watched and completed Lecture 3 of Graph-theoretic models. These suggestions. Of Graph-theoretic models, which is the MIT OpenCourseWare 6.0002 Fall 2016 Introduction to Computational Thinking and Data Science course. This was Lecture 3, Graph-theoretic models. It was really informative lecture. It helped to honestly really solidify some of these more models that I've heard about, put into practice, but actually never really gave a deep dive into what was going on under the hood, and gave the honest effort that it needed to really solidify that information. So this was a good lecture, and I'm happy that we were able to do this. I appreciate you guys for being here and hanging out with me. I am sick. I'm recovering. Today was my first day back in like 5 days. I haven't streamed in quite a while. As you guys can tell by my voice, I am just wrecked, you guys. Today was like the first day that I could really actually use my brain and focus. I did program yesterday offline for for about an hour, and added some features to the Wackathon Stalker project. So you guys can go pull that code if you would like to see it on my GitHub. But man, I've been just wrecked. So I appreciate you guys and your patience, honestly, waiting for me to come back and get back into these. We're going to continue on with this lecture series and finish this course out. But that's going to be it for me today, you guys. I'll be back hopefully tomorrow if I'm feeling up for it. I should be, on the recovery here. I should be only up from here, so thank you guys truly. But man, my head feels like a balloon. I appreciate you guys so much for hanging out with me here. Please like and subscribe if you're new. My name is Michael. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company, and I teach myself how to code every single day, hopefully, when I'm not sick, after my 9-to-5 job as a chemist, and I do that here live on YouTube and Twitch. So thank you guys so much for hanging out with me here, and I'll see you guys tomorrow. Bye, guys. Thanks for being here. See ya.